So next up we have Itumeleng Monageng, who has a joint position here at SAO as well as UCT. He did his PhD at UCT, completed in 2018. And Itu will be talking to us today about a multi-wavelength study of X-ray binaries in the small Magellanic Cloud. So Itu, thank you for joining us. We look forward to it.
Hi, Daniel. Thanks for the introduction. Hi, everyone. Good afternoon. So as you heard, my name is Itumeleng Monageng, and I'll talk about some of the research that I do at UCT and SAO with my colleagues and collaborators on high-mass X-ray binaries. So that's the outline of the talk. I'll give a brief background on X-ray binary systems with a particular focus on high-mass X-ray binaries. And I'll talk about the X-ray binaries in the SMC, show some results on one particular source that we studied, and summarize the talk. So in very basic terms, X-ray binary star systems are interacting binary star systems which consist of a star which is donating some of its mass to its companion star. And the star that is donating the mass is usually referred to as a donor star. And this is a normal star like the sun. So normal as in nuclear fusion is still taking place in the core. And the star that's receiving the mass is usually the remnant of an evolved star. So it can either be a neutron star, a white dwarf, or a black hole, depending on its initial form. So the process of mass transfer can take place via various mechanisms, which are illustrated in the slide here. So we can have rush lobe overflow, where the donor star fills it's what we call the rush lobe, which is a volume of space around which the matter is gravitationally bound. So when this happens, then the mass flows through or funnels through what we call the inner Lagrangian point, and is then accreted by the compact object, resulting in enhanced X-ray emission. In some systems, we have wind accretion. This is when you have a donor star which is blowing off a significant wind, and then the compact object can accrete some of this matter as it's orbiting around it. In certain instances, we have a combination of those two. We have wind rush lobe overflow, where the star itself doesn't fill the rush lobe, but the slow-moving wind from the star can fill the rush lobe, and it's then the matter can then be accreted by the compact object. And in other cases, you have disk accretion, where the donor star has a circumstellar disk from which the compact object can accrete matter from, resulting in X-ray activity. So over here, I'm showing an arbitrary family tree of X-ray binaries. So these are separated into the different subclasses here. So we have high-mass X-ray binaries, intermediate mass X-ray binaries, and low-mass X-ray binaries. So these are the division into the different subclasses depends solely on the type of donor star that's in the system. So when you have a donor star that is a high mass star, so an early type star, we have high mass X-ray binaries. And for a low mass donor star, we have low mass X-ray binaries. So donor stars with masses typically less than a solar mass. And in between these two extreme cases, we have the rare intermediate mass X-ray binaries. So high-mass X-ray binaries can be further divided into supergiant X-ray binaries and B X-ray binaries, depending on the luminosity class of the donor star. So if you have luminosity class 1 or 2, these make up the supergiant X-ray binary systems, whereas luminosity class 3, 4, and 5 type donors, they make up the B X-ray binaries. So for this talk, I'll focus specifically on B X-ray binaries. So this is a movie, I hope you can see it, illustrating what's possibly happening in the X-ray binary system, where you have the B star with the circumstellar disk material, which is variable, as we'll see later, and a neutron star in an eccentric orbit around that, which can accrete matter from the BE disk if it's large enough at close passage, and this results in X-ray activity. The X-ray emission from these systems is characterized by two types of outburst events. These are shown in these example light curves here. So we have type 1 outbursts, which are also called normal outbursts, and we have type 2 outbursts, which are also called giant outbursts. So in type 1 outbursts, they have typically lower luminosities and are often seen to occur regularly and are associated with the close passage of the neutron star, so the periastron passage of the neutron star. And they often cover a small fraction of the orbital period. Giant outbursts or type 2 outbursts, on the other hand, they have larger luminosities. In fact, they can be some of the brightest X-ray events in the sky when they do occur. They're also not necessarily associated with any orbital phase, and they also last a larger fraction of the orbital period. And in some systems, actually, they last for several orbits. So the optical and infrared light in B X-ray binaries comes primarily from the BE star. So it's important to monitor these objects at these wavelengths to get information about the matter that's in the neighborhood of the BE star. And the two main observational characteristics of BE stars are emission lines and in the optical spectra and also infrared excess. So both of these are the result of the presence of the circumstellar disk. So in this slide, I'm showing an example of one source which was in two states. So the blue shows when the source was in a diskless state, and the red shows when the disk was present. So as you can see in the optical spectra, we have absorption lines from the photosphere when the disk wasn't there. And then when the disk was present, we see emission lines. And also in the infrared, we see infrared excess when the disk is present. And so we get Balmer and helium emission lines in the spectra. And the strongest of these lines is the H alpha emission line. It's coming from a larger area of the disk. And we often use this line as a gauge, to tell us what's happening with the circumstellar disk. So over here is a schematic showing a face-on view of the circumstellar disk, and that's the resultant H alpha emission line. So we see the line is double peaked because of the Keplerian distribution of matter in the disk. So in this case, the observer is viewing the disk from below looking up, and we see the double peak profile coming from the Keplerian distribution. So the shaded regions here in the disk mesh those in the H alpha line. So the small Magellanic Cloud, which is our neighboring irregular dwarf galaxy, is quite active in the X-rays, with the majority of these X-ray sources being X-ray pulsars in high-mass X-ray binaries. And the majority of these high-mass X-ray binaries belong to the B X-ray binary population. In fact, the number of B X-ray binaries in the SMC is comparable to those in the Milky Way, despite the Milky Way being about 50 times more massive than the SMC. And the reason for this overabundance of high-mass X-ray binaries in the SMC is most likely attributed to a recent event of star formation due to an enhancement in the tidal force on the SMC from its interaction with the LMC. So this is cool because it makes the SMC an ideal laboratory to study these sources. You have a large amount of them in one place, so you can perform statistical studies on them. It also helps observationally that the SMC has a low foreground extinction. So we know the distance to the SMC very well, so we can get more accurate values of luminosities of these objects compared to the galaxy. So the SMC is monitored in the X-rays by SWIFT through the S-cubed program. So S-cubed is, it stands for SWIFT SMC survey. So this is a high cadence shallow X-ray survey of the SMC. And it consists of 142 tiled pointings covering the optical extent of the SMC. So this is done every week. And each of these pointings has an exposure time of 60 seconds. So it's quite a shallow program. So this image over here shows the S-cube survey with the tiles overlaid on the optical image of the SMC. So the aim of the program is to use the unique capabilities of SWIFT to both discover and monitor X-ray outbursts from the population of B X-ray binaries. Sure. So I'll share some results of one of the objects that's in the SQ catalog with that long name over there. So I'll just refer to it as X0103. So this is a source that appeared in the XMM Newton SMC survey point source catalog, where it was classified as an candidate Hymas X-ray binaries based on its X-ray properties. But it was deemed unlikely to be a B X-ray binary due to the absence of emission lines in its optical spectra. The thing that got us interested actually in this source is this remarkable long-term oval light curve taken over a period of about 10 years. So the top panel here shows the I-band magnitude variations, and the bottom panel shows the V-band variations. And as you can see from the light curves, they have huge outbursts with amplitudes of about 1 magnitude in the I-band and about 0.6 magnitude in the V-band. And these occur regularly with a recurring timescale of about 1,200 days. And they last for about 700 or 750 days or so. So this variability is believed to be due to structural and size changes of the BE disk. And this is one of the most stable and well-behaved photometric variability that at least I've ever seen. And it's one that shows the strongest optical outbursts ever in a BE X-ray binary, actually. So we can compare it, for example, with some of the light curves from a study performed by Henry Rajulimanana for his PhD in 2011. He was at SAO, actually. So you can see the light curves from that study. There's a few examples of them from OGLE and MACHO data sets. So we followed it up with SALT during its most recent optical outburst, where we wanted to look at the optical spectroscopy. So the top panel here shows the blue spectrum with some of the lines labeled. So it's clearly an early type star. And the bottom panel shows most of the optical region, so covering the red and the blue. But what's interesting here is that we see the H alpha line for the first time in emission. So this confirms the BE X-ray binary nature of this source. So following this, we monitored it with SALT further, where we obtained spectra covering the H alpha line region. So this figure on the left shows the evolution of the H alpha line, which is seen in emission since the start of the monitoring campaign. But what was surprising to us were the relatively low equivalent width measurements, especially given the fact that we obtained these during or close to the peak of the OGLE outburst. So in this simple picture that we created for this source, we expected that the unusually large amplitude photometric outbursts would correspond to a very large disk, which would be evident with the equivalent width measurement. So this was quite surprising. Another surprising feature is the very weak X-ray emission as well. So this is, again, the plot that I showed earlier with the two panels showing the OGLE measurements. But at the bottom, we have the X-ray measurements from SQ, so from SWIFT. So the blue symbols show the upper limits, and the black symbols are the detections. So again, the X-ray emission is very low. And as you can see, it covers the last two optical outbursts. So again, with this naive picture that we have for the source, we expected the X-ray emission to be correlated with the photometric emission, which is which is seen with the other systems. So we came up with a qualitative model to explain these observational mysteries for this source in the context of what we call the viscous secretion disk model. So just a quick summary of what this is. So this plot here shows the equivalent width for the different sources. So it's the maximum equivalent width ever recorded for several BE X-ray binaries. And on the x-axis is the orbital periods for these sources. So what this shows here is that there is this truncation. And this is a consequence of the viscous secretion disk model, where we have the neutron star acting like a barrier that limits the extent to which the BE disk can grow. So this results in BE disks that are thicker in BE X-ray binaries compared to the isolated counterparts. So truncation occurs when this condition is satisfied, where you have T versus the viscous torque from the BE disk, and T res is the resonant torque from the neutron star. So when the resonant torque by the neutron star dominates the viscous torque from the disk, then you have truncation occurring. So it seems that our target could be a system in which truncation is extremely efficient, which can happen when you have a system that is of low eccentricity and also low orbital period. So another interesting plot is this color magnitude plot. So on the y-axis, we have the magnitudes showing the brightness of the source, and then on the x-axis, we have the color. So in this case, I'm using the VNI observations from OGLE. So we see a positive correlation between these two quantities, which is an indicator of inclination angle. So for this particular source, it's a low inclination angle relative to our line of sight. As the size of the disk grows, we have excess flux, but we also have the color reddening due to the temperature in the outer parts of the region being cooler. But these can take various shapes and variabilities. So again, I'm using some examples from Henry's study where you see the different shapes of these light curves, or these two quantities. But another feature about this plot is, for our target, is that it has a uniquely distinct looping structure, which evolves in a counterclockwise direction, as shown by the arrows here. And this can be explained again in the context of efficient truncation and the interplay between mass loss from the disk and the outflow of the disk material. So the portion labeled 1 represents the stage where the stellar mass outflow leads to an excess flux and reddening of the system until maximum flux is reached over here. And then once the mass outflow stops from the BE star, suddenly shuts off, then the magnitude drops rapidly while the system still reddens, because at this stage, we're losing the optically thicker regions and bluer regions as well, quicker than the optically thinner redder regions. So this is the point where the disk now has evolved into a ring. But up until a certain point, we have the overall color changing, becoming bluer, because this is the part where we're losing now also the optically thinner redder regions faster than the optically thicker bluer regions. So this scenario can also explain the very low equivalent width measurements seen during the peak of the optical outburst, where line formation is dominant at the very outer parts of the disk. So the long-term brightness changes for the system can be understood in terms of the disk acting as sort of like a pseudo photosphere up until a certain point when line formation can be dominant. So this can explain also the very low X-ray emission that we saw in this for the system. So it appears that even though the optical photometry shows very huge variability, it doesn't necessarily mean that the radius is extending towards the very outer portions of the neutron star's orbit. So it doesn't accrete matter, enough matter to produce any outbursts. So just to summarize, we looked at the optical and X-ray data for this unusual source. We confirmed its BE X-ray binary nature. And we saw how optical photometry shows these huge amplitude outbursts, which are the largest that we've ever seen. But these are accompanied by very low equivalent width measurements and X-ray emission. And we can explain this by invoking the fact that, or proposing that there's a efficient truncation for the system, very efficient truncation. And the color magnitude plots can be explained by the interplay between mass loss and mass outflow from the disk. Thanks.
Thanks very much, Itu, for a great talk. So you've confirmed that this source is a BE X-ray binary. I wonder, what are the next sources that you'll be looking at?
Well, there's quite a few sources in the S-Cube catalog. So there's like over 200 sources. Some of them are known and some of them are mysterious. So we'll have to see.
Is there anything particularly obviously interesting?
Well, I'll have to look at the long-term optical light curves to see if there's anything strange again, similar to this source. And then we can follow them up with SOLVE as well.
Thanks, Itu. So this is a pretty cool multi-wavelength study using optical and X-ray. Can we get other information by using other wavelengths for these objects?
Well, the B X-ray binaries are quite weak in the radio, but there's another set of objects that I'm interested in, together with some people at UCT and SAO, which are called gamma ray binary systems. And we actually have some NIACAD data for a couple of these sources from the previous open time. We submitted another proposal for another source for this round of open time. So there's quite exciting projects coming from those as well.
Great, something to look forward to.
Thanks very much, Itu. That's all we have time for right now.